Now that we've spent some time talking about dot products and inner products, we're going to introduce this idea of orthogonal projection. And just like everything that we've been using recently, there is a kind of a standard way to introduce it, and then you can generalize it as much as you'd like. So let me pose this problem to you. So I'm going to draw. We're going to start with Rn, right? So let's say we have our directed line segments. I'm just going to have things drawn in a way to make it fairly obvious what's going on. But there's our vector v, and then let's say here's our vector u. And here's the problem that we have. We want a third vector, right, that is a scalar multiple of v. So it has to be somewhere. So let me just kind of do this dotted. Right, so we can say that it has to be in the span of v, and we want it to be as close as possible to the terminal point of u. So again, it sounds kind of wordy, but I want a third vector that starts right here, same initial point, and I need to extend it either in the direction of v or opposite to v, so that whenever it stops, it will be as close to this point as possible. So if you think of some possibilities in terms of being close, right? Like if for some reason that vector stops right here, then this would be the distance that I'm looking at. If it stops right here, then it would be, somewhat shorter. If it's like right here, then that will be the distance. And what we want is we want these red lines to be as short as possible. So, intuitively, without doing any sort of special thing, you should be able to see that this red vector should probably stop somewhere around there, so that it actually forms a right triangle with the that altitude that I just drew, right? So it's this red vector that we're looking at, and the only thing that this picture implies is that the red vector is a scalar multiple of my original vector v, right? So we're given u and v, and we have to figure out this red vector. And the other thing that's implied as well from this is that a is positive, right? Now, I could have drawn the picture in a different way, which would imply that a is negative, and it turns out it wouldn't change any of what we're going to do here to kind of figure out what this vector is, right? So the question is, what is the scalar multiple? If I know v, all I need to do is figure out what the scalar multiple is, and then good, I'm good to go. All right, so we know about angles between vectors, so let me draw that angle there. And let's write down a couple things that we know. But before we write down the relationships, I'm going to redraw the triangle, just the right triangle. Get rid of all the colors. It'll be there. If you like colors, it will still be there. But this will be theta. And then since we're dealing with the triangle, I'm going to switch everything over to the magnitude or the length or the norm. So for instance, the base, like I have written there, that would be the magnitude of AV. And then the hypotenuse is going to be the magnitude of U, or the norm of U. Right? So that's what we have right there. And then of course, I don't really need to draw the V thing. But yeah, if you were to draw the v, then it would stop there, and then that distance or length or magnitude would be the magnitude of v, right? Just to put everything in perspective. Okay, so let's see if we can start with the expression that involves the thing that we're trying to figure out, which is a. So let's take a look at the magnitude or norm of AV. And just because of the properties of the dot product, which remember the dot product and the magnitudes and the norms are closely related, we can factor out that a, but technically because of the squaring and the square root, we should take out the absolute value of a, right? It should be like that. But because, just for the purposes of this illustration, because we are assuming that a is positive, then the absolute value of a is just going to be a. So we have a times v. Now, times the norm of v. So then if we take a look at the triangle a little bit more. Since it's a right triangle, and that's kind of what our intuition is telling us, that since it's a right triangle, then I can find an expression that relates, or an equation that relates theta, the length of the hypotenuse, and the length of the adjacent. And with me saying that, you should conjure up images of the cosine ratio. So cosine of theta is going to be the magnitude of AV over the magnitude of U, like that. And look, we just simplified that expression for the norm of AV, so it's going to be A times the norm of V over the norm of U. So like this, norm of U. And then, since we're trying to figure out what the scalar is, we're trying to figure out what A is, let's take this equation now and solve for A. So this implies that A is equal to, so I need to multiply by the magnitude of, or norm of U. So I need to do that, multiply the cosine by that, and then I have to divide by the norm of V, like that. Okay, so that's kind of interesting. Now, the fact that we have an expression that has the norm of U and the cosine of theta being multiplied, it looks very similar. It looks related to the dot product formula, or what we came up with, the relationship, how to find the theta. But what's missing is we need a magnitude of V in the numerator as well. So let's multiply the top and the bottom, right? So let's multiply the top and the bottom of the the right-hand side by the magnitude of V. So we'll have the magnitude of U times the magnitude of V times the cosine of theta, and then this is all over the magnitude of V. Interesting. So that's what our scalar is. But you might, I'm sorry, squared, because we multiplied the bottom as well by the norm of V. But the reason I want to put it in this form is because now this is our dot product, or when we extend it, it's going to be our inner product. So what I'm doing here, I'm just expressing it in terms of Rn. So this would be, so our scalar A, so this implies that A is equal to the dot product of U and V over the magnitude of V squared. Now take a look, let me write this A in one other form. I know there are lots of different forms here, but take a look at this. Since this is a fraction, I'm going to factor the fraction this way. So I'm going to write it as just U, actually, the dot product of U, actually, let me not write that. Let me take this expression now, and I'm gonna take now that we know what A is, I'm gonna take A and plug it back here and figure out what that vector is. Now this red vector is what we describe as the projection of U, the U vector, onto V, the V vector. So we have a nice notation for that because it's so important. So AV is going to be, it has this property, and we call it the projection of U onto V. You can write it like that. Sometimes you might put the U in parentheses. And look at it, it's A times V. So this A that we just found, which is our U dot V over the magnitude of V squared times the vector V. So remember, A is just a scalar, that's just a number, but I'm going to rewrite it in this way. Take one of the factors of V that are in the denominator and write it as, so keep the U dot V there, factor the denominator, take the the norm of V, and then times V over, again, another norm of V. So like, so that's just another way of doing it, right? And notice when you take a vector and divide it by its norm, what do you create? You create a unit vector, right? So you create a unit vector. So this part here has magnitude or norm 1, and then its length, because we're now multiplying it by this scalar, gives me the length of it. So essentially, you can think of in two ways. This part right here gives me the unit direction of this projection. So this gives me the unit direction, right? And then the other part, this part right here, gives me its length. It's a scalar. So, yeah, so this gives me the length of my red vector, all right? And then, yeah, so that's the projection, and then we can actually now say, well, what if we have, what if I have vectors that I can't really represent like directed line segments? Does this still make sense? Does this concept of an orthogonal projection make sense? And the answer is a definitive yes, because we have the concept of an inner product, right? So let's write that down. So let's say that we have U and V in an inner product space with the understanding that V is not the zero vector in that space, whatever it looks like. Then the projection of U onto V is equal to, and now let's write it as, instead of doing dot products and magnitudes, let's write everything in terms of an inner product. So remember, we can replace the dot product with the inner product of U and V like that. Secondly, down here where we have the norm squared, well, that's just the inner product of V with itself. We've used that expression multiple times now, and then over here we have V. Yep. So this is probably the most general and most scalable version of the projection formula, right? And yeah, so let's see how it works. I'll just do an example in R3, and then maybe another example in something like P2, right? So let's do a couple examples here to illustrate how this works. And anytime I'm doing one of these questions in a Euclidean space, unless the question tells me to use some other non-standard inner product, I'm always going to default to the Euclidean inner product, which is our dot product. So for part A, so let's say that V is R3, and let's say that U is the vector. Again, I'm just picking these somewhat at random, right? So there's U, here is V, and then we have 1, 2, 0. All right, so if we want to find the projection of U, I guess that sometimes you can put it in parentheses, onto V, well, the formula says we need to take the inner product of U and V. So for us, that will be a dot product. So I'll just write out the numbers and then simplify it. But it's a pretty straightforward calculation. So it's going to be 6 times 1 plus 2 times 2 plus 4 times 0. That's the dot. That's the inner product slash dot product. And then the dot product of V with itself, that's going to be 1 times 1 plus 2 times 2 plus 0 times 0. And you can see where you get that expression that would show up under the square root of the length, right? So the numerator simplifies to, yeah, just 10. And the denominator simplifies to 5. Oh, I didn't write down my V vector. So let me put V there. And then now so V is 1, 2, 0. So this is 2 times that vector. So again, this is the A that we would have found, right? In this case, A is 2. And then all you do is multiply that vector and that scalar, and you'll get 2, 4, 0. There you go. So pretty straightforward to get that projection. So as long as you can find and you can compute inner products, then you can use this approach to find your projection. So let's try something else. Let's take a look at um, an example in, let's just say P1. Let's keep it pretty simple. And I'm going to use my f of x is just going to be equal to 1. My g of x is just going to be equal to x. And again, we want the projection of, let's say, f onto g. So we want to project the function f onto the function g. Now, when I say that, and you think about the graph of these functions and you're talking about projections, here's what you, let me try to at least verbalize what this idea would mean. What we're trying to do, since we now know, we have a notion of how close functions can be, right, in terms of distance. So what we're trying to find is, if we're projecting f onto g, we're trying to find a function that is a scalar multiple of g that is as close as possible to the function f. So we want multiples of the function x that are as close as possible to the function 1, right, our f function here. But in order for that to happen, then we have to utilize the inner product. So let me define the inner product that we're going to be using. So the inner product, and the question most questions will have to tell you this. So it's going to be just an integral from 0 to 1 of f times g dx. All right, so let's see what we need. In fact, let me write down the expression and then take a look closely at what we need to do. So the projection of f onto g, so our f function onto g, so it's going to be the inner product of f and g, here we go, over the inner product of g with itself, and then times g, right? So because this inner product now requires an integral, there are going to be two integrals that we have to do. So let's do the inner product of 1 and x. That's my f and g functions respectively. So this is going to be the integral from 0 to 1. Just multiply them, right? So then 1 times x is x. And then we do our calc stuff, so we'll have 1/2 x squared, and then we go from 0 to 1, so that just simplifies to 1/2 minus 0, so that's 1/2, right? So that's the inner product of f and g. Now let's take a look at the inner product of g and g, so that's x comma x. Multiply those and integrate, so we'll go from 0 to 1, that gives us x squared dx. When we integrate that, we'll have 1/3 x cubed from 0 to 1. And then again, something pretty straightforward. We have 1/3 minus 0, so we have 1/3. And then putting it all together, right, so whatever this means in terms of closeness, here is the scalar multiple of the g function that is closest to the f function. So our projection of f onto g, it is 1/2 divided by 1/3 times x. So notice it is a scalar multiple of g. So the projection onto g and g itself, those are linearly dependent, but the result is linearly independent of the f function. So we end up having 3/2x, right? So again, it's like we can do the calculations, but I think what helps is when you get into these other more general vector spaces is not necessarily thinking in terms of just, directed line segments, but phrase the problem in terms of like span and closeness, right? So in other words, another way to say that like this, the function that is in the span of g that is closest to our f function is the function 3/2 times x. All right, so let that sink in, and think about your orthogonal projections, and you'll see where, again, we are going to continue to generalize stuff. That seems to be the trend around here. So come back and we'll keep the ball rolling. See you in the next video.